Rachel. Okay, welcome to our class meeting for today, Monday, March the 30th. For those of you that are not in Arizona, our governor just canceled school for the rest of the school year, so my junior is kind of sad. And then, yes, Desiree, she asked, is there a way to record if I can't make the Zoom tomorrow? I always record every meeting that we have. So it will be as soon as it's over, then I post it to YouTube, and then I post it back to Canvas, and so it'll be there. So anytime that anybody can't make it to a meeting, know that it will always be posted. All right.
You're posting them on Canvas?
Yeah, they'll be in the they'll be in the modules. So when you so when I post this one this morning, as soon as we're done here, then go to module 4. Yeah, that's the one we're still in. So go to module 4, and it'll have Monday, March 30th recording, and all of that stuff will be there. So it's always there. Okay, so we're just gonna go ahead. It's 11 o'clock now, so I'm gonna go into our PowerPoint, and so it's our lecture notes, and it's just as if we were in 311-108. Okay, all right, so let me get rid of this. All right, so here, let's wait for that to be real. Come on, there we go. All right. So we've been through all of this information now. This is what we did in lab. So we have all of these definitions. If you haven't seen the lab video that we made for Monday lab, the Romeo and Juliet video, you can watch that. So make sure that you watch that. Make sure that you take the quiz. So let's see, Monday needs to make sure they take the upper extremity quiz, and then everybody needs to take the muscle anatomy quiz. And by, what did I put? I don't remember what date I put now. Well, it's in the announcements. It's on the thing. I'll look for it when we get to the end of class. I'll just tell you guys now, because I forgot to tell this morning class, we're still counting enrollment. Attendance, I mean. And so in order to keep participating in the class, you have to at least take the quiz each week. So if you miss a quiz and you don't turn any homework in, then you're going to be counted as absent for the week. So please make sure you take the quiz and turn in your homework. I'm looking at my chat questions. Okay. All right. So that's how we mark attendance now, is simply that participation, because I'm not taking attendance in this class, in this meeting, and I am not having you send me an email that says, hey, okay, Allegra, let's see. So Allegra, okay, let's see. So, if you can't, of course you can't hear me, of course you'll, okay. So I'm going to double check and make sure that I made the quizzes due for Tuesday and not Sunday. So I will let you know at the end of, at the meeting today. We'll go in and check everything together. Let me hurry and send a message if you can't hear. Go out of meeting and come in again and join with computer audio. All right, okay. So hopefully that will fix her problem. Okay, so here's everything that we've done in lab. Boom, 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 boom. And we did a lot of what we're going to do right now in lab 2, but now we're just going to go through and make sure that we have all of the steps of muscle contraction happening. So we also need to know what is a neuromuscular junction. So remember when we saw a motor unit that we had one motor neuron and then all the muscle cells that it innervates? So the place where the axon terminal, the end of the motor unit, connects to the muscle cell where it synapses with it, we call that a neuromuscular junction. So I'll show you a picture in just a minute. So as we know, because they're skeletal muscle cells, that they are going to be stimulated by motor neurons that are going to be voluntary, coming from your brain, from your cerebrum. The axons will travel from the brain or spinal cord, central nervous system. If it's a reflex, then it only needs to go to the spinal cord and come back. It doesn't have to go all the way to the brain. To the skeletal muscles, they innervate near the muscle, or each muscle fiber has one neuromuscular junction near its middle. So only one motor neuron can innervate a skeletal muscle fiber. So here is the motor neuron coming down. And I don't like how they drew this, because now it looks like it's going to it in 3 different places, but it doesn't. So these other little branches would be going to other motor neuron or other muscle cells. So anyway, but we want to focus on just this one place about halfway through the muscle. So if we're talking about the biceps brachii, it'd be halfway between the shoulder and the elbow is where the musculocutaneous, no, where the axillary nerve will come and innervate the biceps brachii. So if we magnify what's in this little box, here is the neuromuscular junction right here. Now, there's going to be a series of events that need to take place. And the first one we haven't discussed yet. We didn't do it with the lab information, but you absolutely need to know this. So remember that we're going to have some neurotransmitter in the neuron. So here's our neuron. And in these little circles right here, these are called synaptic vesicles. So synaptic vesicles. And inside the little green dots are neurotransmitter. This neurotransmitter is called acetylcholine, or abbreviated ACH. And they just abbreviated it as ACH. They don't put acetylcholine. Okay, now, in order for these vesicles storing acetylcholine to release their acetylcholine, we must have some calcium that's going to be outside of the neuron. We must have it enter. So as the action potential, as the neuron is depolarizing, it's traveling all the way down to the neuron, the bottom of the neuron. When it gets down to these axon terminals, there are these special, let me mark this up a little bit. Okay. So there are these special, in yellow, hopefully you'll be able to see, voltage gated channels right here for calcium. Okay, so the action potential arrives at the axon terminal. Voltage gated calcium channels open. Now we haven't used voltage gated calcium channels yet. And the only job they're going to do for now is allow calcium into the neuron. So let me get a dark green, this a better color. All right. So the calcium will come in, and when the calcium comes in, do you remember those little walkie proteins that we saw in that video a really long time ago, when the big vesicle is being carried towards the cell membrane and it's walking along the microtubule? Well, that's what's going on. And what allows the walkie protein, which happens to be actin, isn't that interesting? Because we know that actin produces movement. So that actin protein is interacting with the microtubule because calcium came in and allowed that exocytosis to happen. So imagine these little circles are being drugged to the cell membrane right here. And as they're drugged to the cell membrane, then exocytosis happens, and the cell membrane of the vesicle will fuse with the cell membrane of the axon, and then acetylcholine diffuses across the cleft, and then it's going to bind right here to this is going to be a chemically gated ion channel. Okay, so right there, each one of these purple things is the chemically gated ion channel. So here's the acetylcholine binding to the receptor right there. And as that receptor binds, then the gate opens up and then sodium rushes in. Okay, all right. So that's the first thing, is that the action potential has to travel down the neuron and then cause the calcium to come in and the synaptic vesicles to fuse with the axon presynaptic membrane, and then the neurotransmitter comes out, and then acetylcholine binds to the chemically gated ion channels, sodium channels, and then the sodium rushes in. So then sodium, this would be sodium coming in here at this point. Okay, all right. Then we need to go to the next point is what is a motor end plate. So a motor end plate is this portion. Just a minute. Okay, so this right here is the motor end plate. So it's the sarcolemma that's all been convoluted, folded like this. But this is only going to be in that one spot in the neuromuscular junction. So we don't see the sarcolemma folded like that anywhere else on the neuron, but just right here where the axon is contacting it. So why do we want to fold it? So we can increase surface area, so we can put in more chemically gated sodium channels right here. Okay, so that's the motor end plate on the sarcolemma. Okay, so on the muscle cell. All right. Okay, so trough-like area on the sarcolemma to increase surface area for acetylcholine receptors found on the opposite side of the synaptic cleft from the axon. Okay, so then we saw neurotransmitter. So there's acetylcholine spelled out, released from the axon terminal by exocytosis. When the impulse reaches the axon, calcium channels open, calcium enters, causes synaptic vesicles to fuse with the axonal membrane, so the membrane of the axon, and release acetylcholine. Here is that happening. So acetylcholine binding opens the channels. Remember we said that sodium, lots of sodium comes in. So in this picture, yeah, I have both happening, but I get lots and lots and lots of sodium in. But then I get a little bit of potassium out. Okay, but really what we want to come in is the sodium. So as it says right here, more sodium ions enter than potassium ions exit, which produces a local change in the membrane potential called the end membrane potential, or end plate membrane potential. So we know that right here at this spot on the membrane, as soon as that sodium comes in, the membrane will now be minus 55 millivolts. Everywhere else is still going to be minus 70. And then over here will still be minus 70. But just right here where the sodium rushed in, it took it to minus 55. So then we know what else is going to happen. Well, these other channels, voltage gated channels here and voltage gated channels here, would then open up and sodium rush in and depolarize both directions. Okay. All right. Now, so we got that. Now, here's the important thing. It says once the acetylcholine diffuses across the gap or the cleft and binds to the acetylcholine receptors on the sarcolemma, it is then broken down by acetylcholinesterase. So acetylcholinesterase is that right there, is an enzyme that is on the sarcolemma. I'll show you a picture of it in a minute, so that we prevent continued muscle fiber contraction. We don't want the muscle to stay contracted. As soon as it's depolarized, we want it to be able to repolarize again. Okay, and so here is acetylcholine. And so, acetylcholinesterase. So here is the enzyme. So once the acetylcholine came and sat down right here, then it's going to bounce out and bounce into the enzyme called acetylcholinesterase, and then it's going to be broken down, degraded. And once it's degraded, then the sodium can't go in anymore and the potassium can't go out. So that allows the cell to repolarize. Okay. So remember, as soon as the acetylcholine binds, the acetylcholine has to be removed by acetylcholinesterase. Yes. Yeah, if your connection isn't so great, then you can watch it because it'll be ready at noon. So if you want to come back and watch it then. Okay. All right. So excitation, contraction, coupling. Sequence of events from depolarization of sarcolemma to sliding filaments. Well, what does that mean? We already know that. That is steps 6 through 15 on the lab paper. Okay, so when the sarcolemma depolarizes, and then the muscle action potential spreads down the sarcolemma, and then the action potential travels down the T system, and then the T tubules depolarize the sarcoplasmic reticulum, and then the calcium is released and binds to the troponin, pulls the tropomyosin out of the way. That is what we call excitation, contraction, coupling. Because what we're doing is coupling, we're putting together excitation. So this was the acetylcholine. And then contraction is myosin binding. So how do we get from acetylcholine binding to the sarcolemma to the myosin binding? Then we couple that together. So that's these steps 6 through 15. Okay. All right. Okay, so this next picture just shows what happens with our membrane channels. And so it's just another graph of depolarization, so an action potential. So here we depolarize, sodium channels close, potassium channels open, we hyperpolarize, we repolarize. This just shows how permeable we are to sodium. So this orange line just shows us we're really permeable to sodium quite quickly, and then we close and we're not permeable anymore. And then this shows, oh man, we're not as permeable to potassium, not as much goes in, and it takes a long time to get in, and then we gradually close the gates. So that's what these two graphs are showing. So orange is sodium permeability and green is potassium permeability. All right, now here is in a picture form, steps 6 through 15. So here the acetylcholine cross the gap, bind to the voltage gated sodium channels, and sodium rushed in, depolarized to the sarcolemma, goes down the T tubules, then the T tubules, this action potential triggers the release from the terminal cisternae of the sarcoplasmic reticulum. That's just these fat places right here on either side of a T tubule. Then calcium ions bind to troponin. Troponin changes shape, removing the blocking action of tropomyosin. Actin active binding sites are exposed, so the little dots on the blueberries now will allow the myosin head to bind. So then contraction occurs. Myosin cross bridges alternately attach to actin and detach, pulling the actin filaments toward the center of the sarcomere, eliminating that H zone, and the release of energy by ATP hydrolysis. So if we go back here, that's what makes it go up. So the ATP molecule would come in, then it would split it into ADP and PI, and then that would allow it to bind and pull. Powers the cycling process. Now, in addition to wanting to get rid of this acetylcholine, we want to get this calcium back out, because as long as calcium is present within the cell, that's also going to allow muscle contraction to happen, and we don't want cramping to go on. So we've got to put this calcium back in here. So there are little calcium pumps, just like there's sodium potassium ATPase pumps, so there are calcium ATPase pumps that are going to pump the calcium back into there. So removal of calcium by active transport into the SR after the action potential ends. So once there's no more depolarization right here, then the pumps turn on and pump the calcium back in. And then tropomyosin blockage is restored, blocking the actin binding sites or active sites. Contraction ends and the muscle fiber relaxes. These guys will still be ready to go. So they've already split their ATP. So they're going to be ready to reach up when they're allowed to grab onto the active sites again. This is what happens when calcium binds to troponin. So here's the myosin head. Here's the troponin, here's the tropomyosin blocking, so you can see that the myosin can't get to that myosin binding sites. So when the calcium comes in, here's there a little bit of calcium's always bound, but when we add this, let me draw this. Okay, So then when we add this calcium right here and we make even more calcium binding to the troponin, it curves the molecule this way. And as the molecule gets curved, look at what happens to tropomyosin. It gets pulled downward into this gap between the actin molecules. So now here is the tropomyosin. Here's the troponin curved and pulling it down that way. And now myosin and actin can bind with one another. Okay. So that's how calcium makes the troponin pull the tropomyosin out of the way. All right. Okay, so we've looked at latent period before. That simply is those events, because we said, why do we have a latent period? Is because we're stimulation or initiation of the action potential to shortening, to contraction of the muscle. So following a stimulus, there's a period of seemingly no activity before the sarcomere shortens or no tension develops. And why is that? Well, it's because it's steps 6 through 15. So remember, steps 6 through 15 were excitation, contraction, coupling. Now the events of contraction are going to be, you know, what we did when the ATP changed the position of the myosin heads, so they reach up and grab. So we'll look at, this is contraction. So you can see there's really short, very few steps in contraction. They just keep repeating themselves over and over and over again. So once an ATP molecule comes in and binds to myosin, it's going to get split into ADP and P. That gives the myosin the ability to reach up and grab onto the actin and to be kind of out to the edges. Then as soon as the ADP and PI leave, then we do the pulling action, or we call it the power stroke or the working stroke. So the myosin has pivots and bends as it pulls on the actin filament, sliding it towards the M line or towards the H zone and eliminating that. Now we're stuck if we don't have some more ATP come in. So we need a molecule of ATP to come in, and so this ATP molecule right here is going to come in and bind right here, because he already looks like this. Because see this guy right here, he's curved up and then he's pointing that direction. So ATP is just going to come in and pop off the binding. So now it's going to come down that way. And now he's back into the low energy head. And so now what does he have to do to this ATP? Well, he has to hydrolyze it. So he has to split it back into these two guys. And as soon as he splits the ATP molecule, then it moves back that way and up so that it can reach up there. So ATP hydrolysis is the process where we break into ADP and PI. So as a new ATP attaches to the myosin head, the cross bridge detaches, and then as ATP is split into ADP and PI, the cocking of the myosin head occurs. We take it back to that high energy conformation or configuration, and we start it all over again. And just think about how many times that has to happen to shorten the muscle as short as we want it to be, or at least the one single myofibril. So that's going to be happening faster than we can even comprehend. And then if we're running fast, if we're trying to do something as quickly as we can, then it's happening even faster than that. So it's just mind-boggling quick how this all happens. Okay, so then if we have no more calcium and we have no more ATP, then relaxation will occur and we'll have no more binding of the actin and myosin together anymore. All right, now motor units. We've already talked about motor units, so we won't have to go through that again. So read through your notes on that. There's a little picture of that. We did isometric contraction already, but excuse me, let's review that. If you watch the lab video on microscopic muscle anatomy and physiology, and the crash course video where Hank's trying to lift the building. So that goes through a good description of the difference between isotonic and isometric. So in the first one, isometric contraction, force builds, we also refer to it as tension, in the muscle, but the muscle neither shortens nor lengthens, and no movement occurs at the insertion. So like he was trying to lift the building, lifting something heavy or pushing against a wall is isometric contraction. So no shortening, no movement is produced. So postural muscles, we always want those to contract isometrically. We want to stay upright. So we know that those muscles, if we're standing upright, we know that those muscles are contracting, but there's no movement that's occurring. Fixators as well, we want to stabilize the muscle, or the joint, we want to keep things in place so we don't get extraneous movements. And here's the important thing, you guys. So remember this, is that cross bridges form, but the filaments don't slide. So what's happening is myosin is reaching up and grabbing onto actin, but they're not pulling actin, okay? And so let's make another little point in here that, let's see, more calcium allows more actin and myosin to bind. Okay, so anytime that we have more calcium present, then we have more myosin and actin binding. So as your brain is telling you push harder, push harder, push harder, what you're doing is recruiting more and more muscle fibers, and more calcium is being released, and more myosin can bind, but there's never any pulling. So no pulling ever occurs. Okay, so that's isometric contraction. Now with isotonic contraction, oh, here's a little picture of it. So here we've got, we hang like a 6 kilogram, so this is 12, 13 pounds. So I have this 13-pound weight on the muscle, it's pulling it down, but the muscle is gonna, if this was like in a live thing, the muscle would be contracting to hold it in place, but it wouldn't be lifting the weight. Okay, so what it's doing, that we hung the muscle, or we hung the weight on the muscle, it produced 6 kilograms of force, because see, that's how heavy that is. So to hold that 6 kilogram weight from dropping, then we have to produce 6 kilograms of force, and we hold it in place. But notice that the resting length, this is the resting length of the muscle. It never changes over time. And then the muscle relaxes. And then, you know, if the weight was too heavy, then it'd tear the muscle or something. But here's the thing, the tension increases and then it decreases, but the length never changes. Okay, so now in an isotonic contraction, the muscle length changes and moves the load. So once enough tension develops to move the load, the tension then remains constant. So if we look at this graph of that happening, here we're going to hook a 3 kilogram weight onto the tendon. And so now we need the muscle to contract to lift, because that's what we want to do. We want to lift the weight. Okay, so we want this to go up that way. So here we produced some force. And guess what, you guys? This right here is an isometric. Because remember, with isometric contraction, we always get an increase in strength. Okay, so here was this portion of the graph is isometric. So every muscle contraction that you do always begins isometrically. But now look at what's happening. The length is decreasing until it relaxes again. So this is it shortening. So this is shortening. And so the force stays constant, stays at 3 kilograms, because that's the weight of the object I'm trying to move. And then it shortens, then we move towards the insertion, and then the muscle relaxes. And after the muscle relaxes, hey, the muscle lengthens again. So let me find my chat purse question. Yes, the insertion is the end with the weight on it. So this is insertion. And when we get an isotonic contraction, the insertion will always be moving towards the origin. And this is the origin. So this is the fixed point of attachment. So if I'm bending my elbow, this would be my shoulder. my scapula, or my humerus, the top of my humerus, and then this would be on my radius. If I'm doing,
SG.
flexing my elbow.
Does every muscle have two origins?
No, it has just some might, some have lots of origins, but we don't worry about that. We just want an origin and an insertion so that we can generalize it. Okay. All right. Any other questions about this? Okay. All right. So isotonic contraction, the muscle shortens. All right. Now, sometimes we can change the amount of force that a muscle can produce by stretching that muscle. And so that's what this graph shows. So what we want to do is maximize the distance or the length. I'm going to pick a color we're not using in here. Okay, so we want to maximize the H zone right here. Okay. So if we maximize the H zone by getting the most actin and myosin overlapping with the most myosin heads, okay, then everybody can pull and we can shorten this whole entire H zone distance. So this is if we are at 100% of our resting sarcomere length. Okay, so this is as stretched out as the muscle will healthily be. But if I start with the muscle partially contracted, look at what happens. Now this is extreme. This took away all H zone, but we have two little, oh, I hate writing with my mouse. I gotta figure out how to do this better. Okay, so we have two little H zone. So we can see, oh yeah, the muscle can't contract a very great distance, and therefore it can't produce as much force. So let's say you're doing bicep curls. And this may be counterintuitive because I know when you want to do bicep curls, you want to keep your arms, you feel like you want to keep your arms bent. But if you straighten out your arms after every curl, you will produce greater force than if you start with your arms partially bent, okay? Because you've decreased the amount of H zone. So you can lift heavier things if you extend that muscle to fully stretched out and then lift. But look at what happens if you stretch it too far. Here I've got a great H zone, but I barely have any actin and myosin binding. And so maybe I'll get some binding between those heads, but that's not enough to pull the thin filaments together. So we don't want to stretch out a muscle. So all the time, if you like tear a muscle, so it's too long, then you will produce very little force. And we can see, oh yeah, here I'm only producing about 30% of the available force that I can. And so this is going to be super important when we get into the heart. So you can know this concept now, but next semester we're going to come in and do it again when we talk about how do we get more force of cardiac muscle when we can't tell our heart muscle to contract harder. Okay. All right. All right. So we've talked about this next stuff in lab, so I'm just going to go through it really quickly. So if we have a muscle twitch, that's where we get one complete contraction and relaxation in response to a single stimulus. Okay, and remember that a twitch has three parts to it. It has a latent period, has a period of contraction, and a period of relaxation. Now, because we don't want all of our muscles to do, well, we have a variety of jobs that we want our muscles to do. And so we have muscles that have different twitch lengths. So we look at these right here. Extraocular muscle, these are the muscles that control your eyeballs. Now you can tell they're going to contract and relax super quickly because we have to be able to follow moving objects even without moving our head. And so we have to be able to move our eyes really quickly. So they have to contract and relax super, super quick. And so extraocular muscles, so your eyeball muscles, move very, very quickly, contract super, super fast, and contract and relax super, super fast. Okay, then we have, and this is really interesting. Okay, so we're going to learn tomorrow that in your leg you have two calf muscles. You have the gastrocnemius and you have the soleus. Now, if we look at the gastrocnemius, it contracts quite rapidly and then relax. Sometimes we refer to them as fast twitch muscles, but I don't like to talk about the twitch part. We do fast, but on Wednesday, you'll see we do it a little bit differently than what we used to designate the muscles. But that's what the fast twitch meant, is that it would contract and relax really quickly. Well, then the soleus is a slow twitch muscle, which means that it contracts slowly and it relaxes slowly. So why in your leg do you have muscles with two different characteristics in their muscle fibers? Okay, so gastrocnemius, really quickly contracting muscles, fast twitch muscles, soleus, slow twitch muscles. Well, think about what you do with your leg. Do you do the same thing with your leg all the time? Are you always running or are you always walking? No. Okay, so what you have when you're walking, you use your soleus more than you use your gastrocnemius. And then when you need to run fast, then you use the gastrocnemius more than you use the soleus. And then your brain is able to figure that out and know that, okay, I want to move quickly, I'm going to use the gastrocnemius. I'm just walking, I'm going to use the soleus. Or if I'm jumping, or if let's say I'm springing off of my tiptoes, then I would use the gastrocnemius as well. Okay, so just depending on what the muscle is designed to do, it'll either contract very, very quickly, pretty quickly, or not so quickly at all. Now, let's go back and remember what happens in these three different periods in a twitch. So the first one, the latent period, is steps 6 through 15. So between stimulation and contraction, when excitation, contraction, coupling occurs. So when the sarcolemma depolarizes all the way down to the calcium and troponin pulls the tropomyosin out of the way. That is the latent period. Muscle tension is beginning. Actin and myosin are going to bind, but they're not going to pull yet, okay? Because the calcium finally pulled the tropomyosin out of the way, and then the actin and myosin combined, but that's where we stop. Then we go into the period of contraction. Now, in PhysioX 2, when you do the testing of latent period length, you're going to find out, and I'm just going to tell you this, but you're going to find out that latent period that never changes. I don't care what muscle it is. I don't care how fast you stimulate it. I don't care how heavily you stimulate it. Latent period is always the same because it always takes about 5 milliseconds for the signal to travel across the sarcolemma down into the T-tubules, release the calcium, and then allow the tropomyosin to be pulled out of the way. So latent period never ever changes length. All right, so then our period of contraction is when the cross bridges are active and the muscle will reach its peak of tension. So my actin and myosin heads have pulled together, and then we got to the end of the H zone, and then we stopped, okay? And then if the tension that we developed exceeds the load, then movement can occur. If I'm trying to lift a building, it will never exceed the load. But if I'm trying to lift a piece of paper, hey, sure. So I get the force being produced, and then I can do the isotonic contraction. And then we relax after that. And so that's with the calcium going back into the sarcoplasmic reticulum and being pumped back in, and then the tropomyosin goes back into place, and then the actin and myosin can't bind anymore. Tension decreases to 0, tracing returns to baseline, and the muscle returns to its initial length. Okay, now, don't worry about these two graphs that are these two different things, external and internal tension. We're not going to worry about that, but just to look at what's going on in these two pictures. I stimulate once, I contract, I relax. Then in a tetanic contraction, I stimulate really, really fast, which means the muscle can't relax in between, and I produce tension where the muscle is not relaxing, and then when I end the stimulus, then relaxation will occur. Okay, So remember we said in lab that sometimes we need different amounts of force being produced by the muscle. So we have to be able to pick and choose how much force is going to occur, so that we're always not smacking ourselves in the head with something because we use too much force, or getting a hernia because we didn't use enough force. Something was heavier than we thought and we hurt ourselves or something like that. So there's two ways that we can alter the amount of tension in a muscle, so the amount of force that a muscle can produce, either through wave summation or multiple motor unit summation. So we'll look at wave summation again, and then if you want to, another demonstration of that happening, Hank did that really good. It's just fast, 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 fast. And so stimuli, so wave or temporal, either one. I like to use wave summation for muscle and temporal summation for neurons, but stick with wave so then you don't get confused. Okay, so stimuli received in rapid succession at the muscle. So faster, 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 faster. What happens as more and more stimuli are being received? More and more calcium is present in the muscle cells, and but remember, if the stimulus comes before repolarization, no summation can occur, because we got that absolute refractory period. But if the stimulus strength is constant and the rate increases, the relaxation time between each muscle twitch, because with each stimulus, you're going to get a twitch. But what we're doing, let's add that. Let's put that in there. Summation, what we're doing in that is adding twitches together. Because every time you stimulate the muscle, you're going to get a twitch. Okay. So the time between the twitches gets shorter, and with more calcium in the sarcoplasm, the force can be higher. So then, and then force, and be greater. All right, so then ultimately a sustained but quivering incomplete tetanus occurs. That's usually what we're going to produce. But if you stimulate it super, super fast, like you're getting tased or something like that, then you can go to complete tetanus. We can't make ourselves go to complete tetanus, but I'm going to show you probably when we come on Wednesday, a little video of that, as close as you're going to get to tetanus in your own self. Let's see. So if all relaxation disappears and the contraction is smooth and sustained, then complete tetanus happens. And I'll show you a graph of that in just a second. All right. But you can't do this forever. You can't do even incomplete tetanus, let alone complete tetanus. Won't go on forever because you're going to run out of ATP. And that's where we get muscle fatigue. Okay. So this level of muscle activity cannot occur indefinitely. So prolonged tetanus results in muscle fatigue where no continued contraction occurs and the muscle tension returns to zero. So here's a twitch, boom, boom. Here's a wave summation. We went up and then we stimulated again and then we went down. But here we're still doing wave summation. So we're stimulating faster and faster and faster. But this is the incomplete tetanus. So let's make a little note. Okay. So let's put this section right here that's our incomplete tetanus. Okay, so that section right there, this down here, this is wave summation. Okay, and that right there too. Okay, so we're stimulating faster, 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 faster. And now this up at the top is complete tetanus. Oops. We have no contraction in between. I mean, no relaxation in between at all. Okay. want to show you some. I'll do this first and then I'll show you something else before we go. All right, so how else can we increase the force that a muscle produces? Well, we can do multiple motor unit summation or recruitment. And so this is, if we stimulate the muscle harder, more muscle fibers are going to be needed to produce the force adequate to move the object or to overcome the stimulus. So increasing stimulus voltage, that's the same as strength. Same as the strength of the stimulus. So it's like banging things harder, you know, hitting the keyboard with your forehead, whatever. So what's that going to do but call more and more muscle fibers into play. Okay, the first stimulus is a threshold. Well, the threshold stimulus would then, when we see the muscle contract, like holding your arms out in front of you. Then if I started putting weights on your arms, maybe I put 2 pounds of weight and then I added another pound. So then I had 3, and then maybe I put a 5-pound weight on. So now you're going to have to hold more, contract more and more muscle fibers to hold that increased force. So as the stimulus strength increases, as the thing that's stimulating my muscle gets heavier and heavier and heavier, all the motor units become recruited. And then stimulus intensity beyond maximal does not produce further contraction. So what that means is that here, at this stimulus right here, that was enough to get the muscle to contract. So maybe I'm bending my arms at the elbow, and then I put a piece of paper on top, and then I put a book on top, and then I put 3 books on top, and then I put 5 books on top. But I may put another book on top. That's not, and I may drop them at that point because I can't hold the weight because I am now at maximal contraction. And if we look at what is maximal contraction, look, then this should say muscle fibers.
Miss G.
Yes.
So when you are straining yourself, trying to hold something,
Yeah.
and your arm is like quivering, is that
Yes.
stimulus, like hitting over and over again, or what is that?
Nope, that's incomplete tetanus. That's your arms trying to relax and your brain saying, don't you dare, you keep holding it. So you're trying to relax, but your brain won't, because you've got to hold that thing in place. So that's when your muscles are quivering like that, that's incomplete tetanus. That's when you know you're really at incomplete tetanus. Okay, so in order to bend your arms to this point, maybe this is all the muscle fibers it took, just 2 of them. Okay, 2. So this is a whole muscle. This is your biceps, for example, is what the circle is. Brachii. Okay. So your arms are down at anatomical position. So then you raise them to 90 degree angle. You bend your elbow. Then I added a book. So it's going to take this one and this one to contract. But do I let go of the other 2? No, because those 2 were holding my arm in place. These, that one and that one, hold the book. So now I put another book on top. So here's holding my arm in place. Here's holding the book, the first book. And then this fiber and this fiber were to hold the second book. And then I add another book on top. And so I'm still contracting the same ones that I've had contracted all this time, but then I contract more to hold the rest of the force. By the time I get to the most that my muscle can hold, all of the muscle fibers are contracted now. And then I can get to tetanus that way too. Okay, now, when we were doing the lab thing with the Hank video, he was talking about how different size muscle fibers are used. And so whenever, we always want to do as little as possible first. So typically we're going to recruit our smallest fibers to do a job. Then if the job requires more force, then we'll use bigger fibers, okay? Because fibers, we're going to find out on Wednesday, come in different sizes. So then I can use the medium fibers, and then I'm going to use the large fibers last, because they're going to produce a heck of a lot of force. And maybe I don't quite want that, that I want dexterity instead of force. Oops. Okay. All right. So we're not going to watch the video. So there's a video that's in here. We'll watch that on Wednesday. So let's just do TREPA and then we'll be done for today. All right. So TREPA is almost like wave summation, but not, because when you do that, when you do TREPA, notice that, oh, I didn't put that in the definition, that the muscle returns to its original resting length. Let's put that in the, in here. Let's put muscle relaxes in between stimuli. Okay, so what does that look like? And then we'll come back to this. Okay, yes, so Camilla just asked, motor unit recruitment is affected by stimulus strength only and not time? Yes. Okay, so multiple motor unit recruitment is stimulus strength. Wave summation is time. So the shorter the time between stimuli, the more the muscle will be contracted because it doesn't get to relax in between. Okay, so multiple motor unit summation, stimulus strength, wave summation, stimulus intent, or stimulus frequency. So faster and faster and faster. All right, so let's look at TREPA here. And there we go. So notice that in between each contraction, there is complete relaxation. Then I contract it again, and then I relax. So I'm not contracting this any faster, nor am I contracting it any harder. But I get an increase until I get the tension that I'm after, because my muscle has finally warmed up. And so the enzymes are working more efficiently. The muscle can contract the way it's supposed to be for that particular stimulus. So heat is generated, enzymes become more efficient, muscle more pliable. And this is why athletes warm up before a competition or game. Okay. And there is a little bit more calcium available, but not like we have in wave summation. This is just the same contraction. It just happens to get a little bit better until we get to what we expect with that stimulus. Okay, last one we're going to stop for today. So we're going to do muscle tone next time, and then we'll look at, I'm going to post, I'm just going through what we're going to talk about. Yeah, I'm going to post a handout that you should download for Wednesday on the different muscle fiber types and how they do things differently. And then we'll watch a video on that's in this spot. Oh, I need to post the PowerPoint too, so that you could click on it if you wanted to go back and watch it whenever. So, oh, that's a gross picture that it started on. So we'll watch this video because it's really kind of fascinating. All right. So does anybody have any last minute? So yes, lab is tomorrow at 1 o'clock. Get out of here, stop sharing. There we go. Yeah, so 1 o'clock tomorrow. Oh, I know, Abby, we need to look at when's the quiz due? Okay, so, okay, so if you go, here, let me share my screen. Okay, so always go to module. This is where I'm going to have everything so you can find it. So we're in module 4. So, so Tuesday, you need to have the microscopic, because we did it last week. And for the Monday people and the Thursday people, you guys did it way before spring break. So get that done by tomorrow at 11:59 p.m. So you have all day to do it. And then notice that exercise 13 isn't due yet because we started it way, way, way long time ago. And, but we still haven't finished it yet. So, okay, was there another question? then you just, okay, remember you guys, always and forever, I'm recording this right now. I record everything, and as soon as the meeting's over, then I post it into Canvas. So it will be, every meeting we ever have will be recorded and will always be in Canvas as soon as I'm done. So, okay. All right. So is there, it'll, in the modules, that's where I post it. Yep. So it'll be, let's see. Oh, this is, oh, this time I put the video, where is it? There we go. I put the video in here. Oh, right there. Muscle physiology video. I put in announcements, but from now on, all the videos will be in the module. So you don't have to keep scrolling through announcements to try to find them, because that's a pain. Okay. Thank you. Yay, Trey. I'm glad you're here. I saw your mom and dad the other day. So they wanted to make sure that you knew what you were doing. And I said, oh yeah, we'll be on here. And yay, Allegra. I'm glad that, did you get your sound okay? I'm guessing. So, okay. All right. Perfect. Okay. Any last questions before we go? Hi, Danya in Utah. I'm guessing that's where you are. And wherever else anybody happens to be.
Hi, I definitely am in Utah.
Oh, good. Good for you. I'm glad you can be home.
Me too.
That's excellent. Okay.
Thank
Well,
you.
yep, you bet. Okay, so I'm going to stop the recording and then end the meeting for everybody. So we'll see you tomorrow at 1 o'clock or whenever. Okay, bye.